All right, so I told you all that this session was about debugability and observability, and I bet you thought I was talking about cores and bytes per second and CPU efficiency. Um, so this is another kind of observability, a little more along the terms of money. Uh, so the last talk of the session is cost analysis of running a compute center. Yeah.
Hello, hello. You can hear me? Good. Yeah, hi everyone. My name is Zhangqiu Wang. I'm actually a physicist, a postdoc at MIT. My name is quite long, so you can just call me Cheer for short. Yeah, I had a quite different topic today. I'm gonna talk about money. So here is today's outline. Our basically consists of three major parts. I'll first talk about introduction, and then I'll talk about details of the holistic cost analysis that we use to conduct it using the MIT Tier 2 Center. And then I'll translate to a more general usage, talking about the general way and a general tool to have this cost analysis that everyone could use to apply to a different computing center. Okay, so over the years, the demand on the computing resources has significantly increased because we have a much larger volume of data coming in. We have more various of physics models to simulate, and especially with the recent AI development, that the corresponding application is also going on. So when we talk about the computing center, apart from the traditional performance metrics, there are more factors to consider. One of them is the power consumption, because this will also go much higher with the increased demand on the computing resources. And the cost of the power consumption has now become one of the key contributors to the operational expense. And usually everyone knows that with the new hardware, there is always the advantage in terms of the power efficiency. But it is usually unclear for us that what is the point that we should and to retire the old hardware and to replace with the new one. So we did this analysis and hoping this could help with nowadays computing center with their redesign to align with the power efficiency and the sustainability goals. Okay, so the cost consumptions of running a computing center is quite complicated. It has three major parts. Traditionally, we consider the purchase of the hardware itself. And there's also a space usage, which usually reflects in the maintenance of the rack. And the reasonable value for that is about $5,000 a year to maintain a 40-unit rack. And there is a major one, which comes from the power consumption. The power consumption has two parts. One is the power that is actually used by the machines themselves. The second part comes from the cooling system. It reflects how well the cooling could dissipate the heat. And usually people use PUE, which is the power usage effectiveness, to reflect that. This is defined as the total power used by the site divided by the power actually used by the IT equipment. So for nowadays, the computing center usually has a PUE value around 1.5. And there could be some really advanced computing sites that has the PUE as low as 1.1. Okay, so since I used the analysis on Tier 2 Center, here is a brief introduction. So Tier 2 Center is a high-performance facility that is dedicated to reprocessing, storing, and analyzing data for CMS, LHCb, and some other small experiments. It has about 700 machines, providing about 25,000 CPU cores and about 16 petabytes of storage. So far, the site is using a mixing model where we combine the computing and the storage system together. And currently, we are doing some redesign to separate them apart. And thus, we conduct this analysis to give us a guideline of what kind of old hardware we should retire, and so that we could prepare for the future high-lumen LHC, and also to improve the power efficiency and to minimize the future expense for site operation. So Here I'm going to talk about the details of the cost analysis. So among the MIT Tier 2 Center, we have different types of CPU models. In the table, you can find the full list of the CPU models that we use in this cost analysis. We have some very old hardware back more than 15 years old, and they kept working. So we kept them and we use here for this exercise. We have the hardwares across almost 20 years. And this is the latest one, which was produced like 1 or 2 years ago with a process node of 5 nanometers. And here, and also the process node in the table across a bunch of range up to 65 nanometers. You can also find their corresponding H-spec value and the number of cores per machine. So for the latest one that we use as a new hardware has about more than 500 CPU for each of the machine. Okay, since now we want to do a cost analysis, we want to measure the power. In order to make sure that the power that we get is reliable, we need to make a cross-check. The power that comes from the monitoring comes from basically 2 software packages. One is IPMI tool for most of the machines, and OM report for Center 7 machine. To make sure the value from those softwares are reliable, we make a cross-check using 2 example servers, and we did different measurements using manual measurement, using clamp meter and AC splitter, plugging on the machine and to measure their current. So we cross-check the current with whatever given by the monitoring, and we also basically load the machines with different scenarios using stress test command, load different number of CPUs. We also load them with the actual CMS workflows, loaded about 16 and 32 cores. So under different scenarios, we found that the current given by 2 methods are very consistent with each other, which means that the power reading that we got from the monitoring is reliable, and then we can move on. So here is the power usage at Tier 2 for the realistic operation for CMS for different CPU models. The data are subtracted from 2 months of operation back in December and January. So the first thing you probably would see is that the power consumption is relatively stable in the actual operation. It's mostly flat. You can only see that there's a huge difference because this is when the power glitch happened. So here we are using the data from the plateau to do this analysis. And secondly, we want to check how the power consumption is correlated to the CPU usage and other usage. On the top right, you can see this is the CPU usage in percentage for different CPU models. Bottom is the memory usage for the different types of CPU models. You can see that there is a strong correlation between the CPU usage and the power usage. You can also see the dip in the power glitch. For the other usage, like a disk usage, we don't find a very strong correlation to the power consumption. The second thing is that the proportion between the CPU usage and the memory usage is relatively similar among different CPU models. It is found to be about 1.2 gigabytes per core. So to evaluate the power efficiency, here we use the amount of power that you use to provide a certain amount of H-spec value as a metric. And probably the third thing you will see is that among different CPU models, they have a very different CPU usage efficiency. And here is a more direct look for those different CPU models. So for the hardware that is less than 5 years old, it typically has a very good CPU usage utilization. It has the CPU efficiency at about 70 to 80%, and this is consistent with the CMS production. As for the older hardware, which is older than 6, 7 years, you can see the efficiency drops below 50%. This is mostly because those hardwares are older, so they have a lower cores per machine, and it doesn't suit the modern requirements of the computing, because this is for the CMS specific, because CMS pilots production comes with 8 cores. And also because of the fragmentation issue, it is harder to fill with the machine that has lower cores. And this is what we got. But if we use only a single core jobs, probably those could be better utilized. So here is the transition from the CPU usage to power versus number of cores. So this is the power you need to provide a single core computation for different CPU models. You can see their production year from the oldest to newest. On the right side is the latest CPU servers which we want to replace them with. And also from this plot, you can already see there's a huge difference between different types, especially for the old one. And here is the power that you need to provide 100 HSPAC computation. The difference is even larger. Take the oldest hardware, for example. They are almost more than 2 orders of magnitude different. There are a factor of 10 times comes from the low CPU usage for the low core machines, but there are about more than 20 times difference that comes from actual power consumptions from the hardware. You can also see that even for the hardware that is 7, 8 years old, the difference to the newest one is also more than an order of magnitude difference. Okay, so now we have the power. This is the full power of the tier 2 center that is measured from the monitoring, sum up together. And this is the power used for the full sites. Of course, there are also other computing servers that are not accounted for in this plot. But as a major power consumer, the tier 2, you can see there's a very strong correlation between the tier 2 power usage and the total site power usage. Here is the overlay, which I just scaled the tier 2 power usage to overlap with the total sites usage. You can see they are strongly correlated. So now we know the power efficiency. We want to translate this to the cost efficiency, and this is how the calculation is done. We use some estimation, and we include the cost coming from the power, coming from the space, and coming from the cooling. The power price we use typically at MIT site, the price is about 16 cents per kilowatt hour. And the PUE is about 1.4, which is the typical samples we use. And space usage is $5,000 per year for a single rack. So yearly cost will contain the price you pay for the power plus the price you pay for the rack. And here is one example of how many money you need to spend to provide 100 HSPAC computation. For the newest hardware, which is a process node 5 nanometers, usually if you want to replace them, you will need to spend $600 to purchase the hardware, and it's only about $42 per year to maintain the operation. As we go to the oldest hardware, which is 65 nanometer process node, this cost is extremely high, which is $14,000 for 1 year operation. If we replace this with the newest hardware, then it means we only need to wait for 2 weeks before the sites start to save the money. So if we use a stronger word to describe this, then keeping them running is already a sin. And then similar estimation is done to other CPU models. And here you can see the summary table. In the histogram, you can see how much money you need to spend to provide 100 HSPAC computation every year. And you have the corresponding production process in how many nanometers. And in the table, you can also see the break-even time, which means like how long you replace them with the new hardware, then you start to save the money. So here you can see for any hardware that is older than 6 years or 5 years with the process node larger than 30 nanometers, we should replace them because the break-even time is just a few months. Well, as for the newer one, the break-even time when it's several years, then okay, we should keep them. We should wait for a newer hardware and just wait for a few more years. And also, this is currently what we are doing right now at MIT Tier 2. We are already starting to get rid of all those old hardwares. Okay, so now we have a specific analysis on MIT Tier 2. We want to transit this to a more general use case. This is our idea that we are interested in, and this tool is still under development. So the idea is to have a tool that could access the computing hardware and then suggest a cost effectiveness upgrades. This is essentially a Python package. And then it will go with a web interface where people could put their input variables, their conditions of the sites. It will have the information of what CPU models they're using, the power price at their sites, the cooling system, how well they are, and which rack type they're using. So once they have put this inside, the software will fetch the existing database and to analyze which hardware type they're using and how much power they're gonna take under a certain amount of CPU usage efficiency, and then break down the cost in terms of those compositions. And then as an output, it will tell you like how much of the new hardware that you need to purchase to achieve the same amount of computation power, and how much money you could save with those upgrade plan. And at the end, it will give you an upgrade recommendation to maintain a performance at a reduced cost. So here is the master equation. I won't go too detailed about this, but here it has contained the price you need to pay for the power consumption, the price for the rack. As for the CPU model related parameters like H-spec of the hardware, the power consumption, those are determined from the database. All you need to do is to input like the efficiency the CPU efficiency that you run at your operation time, the PUE, and which type of rack you're using. And then it will compare the cost with the new hardware purchase and give you the final recommendation. Here we did this on relatively smaller sites. We did a real world application on MIT Tier 3 sites. This is a relatively smaller site with only 1,000 core, and it only has 3 different CPU types. And this site has a different operational pattern because it's a relatively small site, and only users are using the sites, so it operates at a relatively lower CPU efficiency, which is at 40%, and it could reach to a 0 CPU usage when there's no one using it. The PUE is set to be 1.4. The power price is 14 cents. And on the right side, you can see the output. So it will give you how much money you need to provide a certain amount of computation. You will compare your existing hardware with the newest hardware, and you already see that there is like 50 times difference between the old and new hardware. And then in the table, it will also provide you the break-even time. So here, for example, we should replace 65 nanometer process node, and we should maybe also replace the 32 nanometer node. So that brings me to the end. As a summary, I presented the holistic cost analysis of running a computing center. And among them, the cost of the power consumption can be enormous, and it highly depends on the hardware and its age. Even for smaller computing setups, it could draw a tremendous amount of power. So old hardware should be replaced in order to achieve a long-term, to minimize the long-term operational expense. And the rough guideline is given. So for any hardware that is older than 10 years, they should be replaced immediately. For the hardware that is older than 5 years, they should also be replaced because typically the cost saving with the new hardware could be realized within 1 to 2 years of operational time. And then at last, just to provide a general way that people could use to conduct this analysis for any of the computing sites. And that's all. Thank you.
And thank you for this refreshing view. Two questions. First of all, do you take into account the if you keep the money in the bank, what is the return on this and how it relates to, because hardware on the floor is hardware on the floor. Money in the bank can give you 4%, 5%, and it's not clear to me. So that's something you may want to consider, that especially when you talk about 1 to 2 years return. The other one, just sort of out of curiosity, do you as a CMS see the power bill? I mean, do you guys pay for it or the university pays for it?
The first question is, the short answer is no. But if we want to consider this, is just to add an additional factor inside this equation. It should be straightforward, but still as a recommendation for very old hardware, there's far more beyond interest from the bank.
I understand the 10 years, but I understand the 15 days. But when you look at 1 to 2 years, there is a money cost for paying it today rather than paying it in 2 years. So you may want to consider it.
Yeah, yeah. But yeah.
Sometimes banks go out of business as well, you know that.
Yeah, so, and especially in the world of academia, that you're spending money that you don't have. So you may have to take a loan to pay for it. Don't put it on your credit card, because the 20%, it's not a good idea. But do you, as CMS, see the electricity bill, or is that coming from the university?
I'm actually not sure. I'm leaning towards the university is paying for this. Yeah.
So that brings in academia the total cost of ownership is tricky, because it's being paid from and nobody pays also rent for it. But okay, thank you for the presentation. It's a great thing to have this in the mix of our consideration.
Capital equipment doesn't incur overhead, therefore electricity is free. It's well known.
Yeah, but I don't want to get here into the question of, is the cost of electricity flat, or can you fluctuate? I mean, can you run more at night and less during the day, and things like this that can change your power bill?
Oh, thanks. I remember when they first came out with the smart PDUs. Do you or have you considered using those to gather power consumption data, like the APC PDUs? You can plug them into an Ethernet port and get SNMP traps from them and stuff like that.
Sorry, you mean small PUE?
No, the power distribution units on the rack.
Yeah.
Mm-hmm.
Yeah, I think we have this a maximum power supply of each rack, and that is in the consideration, at least in the master equation. Yeah, but to be honest, the price coming from the rack is relatively negligible compared to actually you pay for the power bill.
Right, right. Thanks.
Yeah.
Do you have any idea of how quickly CPUs have been becoming more efficient over years? Like watts per output?
I mean, it depends on the jobs from the people running, because if it's running the single core job everywhere, then the CPU usage is relatively stable among different CPU models. I think the major difference comes from multi-core, because nowadays in the production that people tend to have 8-core jobs or 16-core jobs coming in, and that will largely affect the low-core machine CPU efficiency. But I would say if it's just for the user, that everyone runs single core is relatively similar. The only difference comes from how many of each spec provided by each core. That has some difference among different CPU models, but that's about 30% difference roughly among different types.
Liz?
Yeah, this isn't really a question. It's a comment from Marone's. He invoked CMS, and I would say that it's very different for the rest of CMS compared to the US. And in fact, there's been a lot of talk internationally about the carbon cost of computing. And, some of the conclusions that came from that were that if you are living in a place where energy is green and costs little, as in some of the Nordic countries, then you should hold on to your CPUs as long as possible. And if you come from Germany, because they have really expensive and very dirty power there, then yeah, you should be buying every couple of years, basically. This doesn't really apply to the US so much because ours are kind of in the middle. We're not particularly dirty and we're not particularly green like France. But for us, exactly because the universities eat that cost, for us, it's much more the total cost of just the CPU part and GPU part. Of course, our needs in the longer term are such that we might run out of power and cooling at universities, or they might finally say no, at which point we'll have to reconsider.
I was just going to add two comments to something Marone alluded to. We have this problem. Electricity is very expensive in Hawaii. There's no forcing function. The CIO gets the bill. We have a very large presence in the data center. Someone else gets the bill. The project purchases, one particular project with a very large footprint, purchases 8-year-old used hardware, fills up the data center, and something that your formula doesn't really capture is the scarcity or availability, the cost of the footprint right? So I've got one user that's got really old hardware and it's really cheap for them to purchase, but they're using up electricity and they're using up scarce cabinet space. And there is a cost to that, but we want to be able to have a forcing function actually to help these projects do better.
All right. Somehow we accidentally scheduled a relatively short break. So we should thank our speaker again.